Hi guys, I'm glad to share our work on encrypted database, and our efforts is to make it secure and maintainable. My name is Mingyu from Shanghai Jiao University and AI Lab, and this is a joint work with Northeastern University and Alibaba Group. Suppose you're using a database which stores your sensitive data, like your financial reports or health records. Your data is so precious that there are many bad guys trying to steal it. Is there any approach to protect your data from data theft? Trusted hardware, or TEE, offers a black box against this to protect your data from theft. The basic idea is to put the database system inside a TEE, which makes an encrypted database. We call it encrypted because everything outside the TEE black box is encrypted, including your sending SQL and the return results. Unfortunately, this kind of EDB might have bugs during runtime. For example, some misconfiguration bug or deadlocks might cause slow query. And these kind of bugs are typically handled by experts, namely database admin or DBA. However, the TEE black box prevents DBA from accessing its internal, which prevents maintenance. This is why Type 2 EDB comes into place. Type 2 EDB consists of a DBMS engine and many operators running inside the TEE blocks. The operator covers many basic data types and common operations. So the data inside the TEE blocks for the ops are in the form of plain text, where the DBMS processes data in ciphertexts. This ensures data privacy. Also, the DBA can access the DBMS states, which preserves maintainability. This kind of EDB architecture is adopted by major cloud DB as a service vendors, such as Azure and Alibaba. Let me give you a more concrete example of how Type 2 EDB works. So both the user and the ops running inside a black box host an encryption key, and everything in the storage is encrypted. First, the user will send a query whose constants are encrypted, like in this case, the city name is encrypted. And the DBMS receives the query, parses the query, and he knows he needs to load the table of customer. And since you need to process the summation of balance, and all the data of the balance column are encrypted, it sends the ciphertext as well as the operator to the TEE black box. And ops inside first decrypts the cipher and then perform the computation. And finally, encrypt the results and send it back to the user. Oops, we find a very severe attacks named the smuggle attacks. This is because the operators, they can be manipulated by DBA. So first, the DBA will choose a random secret value from the victim and use the division operator to get the ciphertext corresponding to 1. And then use addition to construct a sequence of non-ciphers. In the end, he can use the equality operator to compare every single secret value from the victim. In order to speed up, he can even use binary search. Compared with prior EDB attacks, what makes smuggle stand out is that smuggle requires zero background knowledge or prior knowledge, which is very powerful. So here we are in a dilemma. We have Type 1 EDB, which is secure but cannot be maintained, and Type 2 EDB can be maintained but is not secure at all. How can we resolve this dilemma? In order to answer the question how to build an EDB with both security and maintainability, we need to face or tackle 3 challenges: defend smuggle, maintain DBMS, as well as ops. Let's get started from the first one. So we find that the DBA, they will test their ideals using the standby, because today's database system, they use replica architecture, either primary backup or primary standby. And DBA test their ideas using a standby before they apply the fix back to the primary. This inspires us to isolate DBAs from the user's EDB instances. Here is our proposal, HiDB. HiDB is a 2-mode EDB architecture. One mode is execution mode, and the other is maintenance mode. So in the execution mode, user issue queries as usual. And in order for the DBA to maintain a database, we use fork. And this is not simple fork, we use VM fork. Because some errors are within a database, like deadlocks, and some are from the operating system, like the file system errors or network misconfiguration. As a result, the DBA can access the DBMS state. So this architecture, as the ops are not open to the DBA, it ensures security, and the DBA can access the DBMS internal errors, preserving maintainability. Sometimes the DBA needs to re-execute queries, user queries, to ensure their updates really take effect or works. So the challenge here is that since the ops are not accessible by the DBA, how to mock the operator invocation if the DBMS in a maintenance mode needs the operator. HiDB takes record and replay approach. And basically, in the maintenance mode, HiDB replay the execution trace, the ops invocation trace, in the form of ciphertext, which preserves user privacy. Let's talk about the second challenge, how to fix the DBMS bug here. So we divide the DBA task into two steps. Step one is inspection. The DBA might install providers or attach debuggers. The step two, the DBA will propose a fix, such as modifying configuration files or rebuilding indices. We find that both inspection and fixes, these two steps, will modify the DBMS state. When we cannot simply sync it back or fork the state of DBMS in a maintenance mode into the execution mode, because the DBA might install backdoors to perform, for example, smuggle attacks. How can we tackle this? In order to solve this problem, we performed an empirical study summarized from 50 experienced DBAs and 8 popular databases. And we find that the asymmetry of the inspection and fixes. For the inspection, the DBA will diagnose the symptoms, and we find that they are quite random, arbitrary, and complex. Whereas the fixes, they are quite regular and structured. Usually, a DBA needs to specify a particular parameter or argument using an existing script. So this inspires us to be quite open for any inspection, but very restrictive for any fixes. So here's how HiDB works. First, we fork a DBMS instance into the maintenance mode. And then we allow DBA to perform trial and errors using the clone state. After the DBA finds the root cause, we discard the inspected and fixed instances because they are modified. And then we allow the DBA to submit a template containing the fix. And HiDB inside execution mode will check or filter invalid values in a template. And only if the value is within a legitimate range, the fix will be applied. Then is the last challenge. Still, the ops inside the TE box might have bugs, and the DBA cannot access it. We cannot use fork like we do for the DBMS because it contains user secrets in plain text. What are we going to do? So our observation is that to ensure crash consistency between DBMS and ops, the ops are designed to be stateless. As a result, its control flow only depends on its input. If two inputs, they can trigger the same bug, we call it control flow equivalence. In fact, there are many inputs that can trigger the same bugs. So this inspires us to hide user secrets using control flow equivalence. The basic idea here is that to generate a pair, and then we replace real input using the fake input. And then how can we generate such one? We can use concurrent executor like CLE to transform a real input into control flow. And then we can use constraint solver like Z3 to convert control flow back to a new input. The problem here is what kind of fake inputs are secure enough? Let me give you an example. In this case, the generated fake inputs is partially similar to the original one, which still leaks the area code. Maybe try another one, but how many times? Our observation is that in modern data center, there are data masking engines, and there are already quite a lot of data masking rules ready to use. And the user can choose whatever they need to mask their data because they know the semantic of their data columns. And we send these masking rules to the constraint solver to generate only one new fake input. Because of the control flow equivalence, the block can be reproduced. And the masking rule ensures privacy. And only one fake input needs to be generated, which ensures efficiency. In this case, the newly generated fake input, both the fake input and the pattern in the like clause are masked in order to achieve this control flow equivalence. Let's put everything together. HiDB is a two-mode architecture. In the execution mode, user issue queries. For the DBA to maintain a database, HiDB uses, but DBA cannot access the ops, which prevents Mago. In order for a DBA to maintain a database, HiDB uses fork, record, and replay. And HiDB also uses control flow and masking rules to generate fake data for DBA to maintain ops. We built HiDB using real-world hardware. It should be noted that HiDB is quite portable because the abstraction of confidential VM used in EDB is widely available on today's trusted hardware. To evaluate HiDB's maintainability, we performed empirical study in 6 months in Alibaba data center by collecting 28,000 tickets from users. And then we classify 4 categories of DBA tasks, 1 control plane and 3 data plane. It turns out that HiDB can cover common daily tasks with one exception. So the query writing of DBAs, they might generate new invocations of operators, which can be treated dangerous. To evaluate HiDB's cost, we use TBCH as the representative workload because TBCH involves sum, average, group by, whose operators can be used to conduct Smago attacks. And the runtime cost and storage cost of TBCH is quite acceptable. The replay is even faster than the real execution because it avoids real encryption and decryption. Before we summarize, let me iterate the main contribution of HiDB. First, we survey state-of-the-art encrypted databases and classify them into type 1 and type 2. And then we discover an effective and efficient attack to the real-world type 2 EDB named Smago attacks. And then we perform empirical study of modern DB operations. And based on our study, we built a new system, HiDB, enabling DBA tasks without compromising user secrets. So HiDB is a two-mode EDB that supports both maintenance and security. Nevertheless, it's not perfect. We plan to support query writing, DBA tasks, and also cover concurrent write workloads such as TBCC. We have made HiDB open source, and if you're interested in building, no matter either type 1 or type 2 EDB, we include tutorial there. And thank you very much.